let's revisit the condition of the increment of plastic straining that we started off with. So if we had plastic straining in our problem, then under an increment of plastic straining, we saw that the change in the yield function dF was equal to 0 because the stress would remain at the yield surface. So we can invoke the condition of dF is equal to 0. So if we go back to the equation that we defined before for F as a function of sigma, alpha and Wp, then we can write here F is a function of sigma, alpha and Wp. Then during an increment, if dF is equal to 0, then we can write this equation as, let's write in at dF is equal to 0, we can write dou F dou sigma transpose d sigma plus dou F dou alpha transpose d alpha plus dou F dou Wp times dWp is equal to 0. Now if we substitute now the definitions for the flow rule and the isotropic hardening and the kinematic hardening into this equation over here, then we can write this as, I'm not going to go through all the details, but you would get the relation of d sigma to be equal to E times the total strain increment minus the flow rule behavior, which is dq d sigma times the plastic multiplier. The dWp would be equal to the stress times the flow rule behavior, and the d alpha would be equal to C times the flow rule behavior with alpha. Let me write this cleanly. These expressions can be now substituted into the relation before that I've shown you here. So let's call this relation 1. And all these terms, I don't want to write the term here. So all these terms, let's say equation 2, can be substituted back into 1. Substituting 2 into 1. I'm going to write on the following page. We will, once we substitute everything, I can write it in very simple terms as d lambda, which is the multiplier, the plastic multiplier, will be written as p lambda times the total strain increment, where p lambda can be written as, in a very complicated way, dF dou F dou sigma transpose times the elastic modulus divided by dou F dou sigma transpose E with the flow rule dou Q dou sigma minus dou F dou alpha transpose C dou Q dou alpha minus dou F dou Wp sigma transpose dou Q dou sigma. So that's the definition of the P lambda, which is a row matrix. Now, although you can see that both work hardening and the strain hardening are included in this equation, practical applications will use one or the other, okay, or maybe a fraction of both of them. So maybe a combination can also be used. So finally, what we can write, when we started with d sigma as the E, the elastic plastic definition, so we have EEP for elastic plastic, not just elastic definition, then it would depend on the total increment. Then in this case, the EEP would be written as the Young's modulus for, or the elastic modulus with identity row matrix minus the flow rule behavior times this P lambda. Of course, we can go about describing everything, but the idea is that from the equation that we had, from all the relations that we described one by one over here, and the substitution that we get for P lambda, If we continue working this out, then we will also get that the elastic plastic modulus is a function of the elastic modulus, the flow behavior, as well as this rho matrix, which contains both strain hardening and work hardening. So it can be regarded basically as a form of a tangent modulus. Yeah, it's quite similar to, let's say, a tangent modulus that we work with in incremental stress for nonlinearities. It's a symmetric matrix with a following an associated flow rule. And for unloading, we know that dF will be less than 0. And for a yielding state, the F will be equal to 0. And it would be less than 0 when yielding does not occur yet. In that case, you can just set, you have to just set it, the P lambda to 0, so that you can get the EEP to be equal to E. So easily when you can say when F is less than 0, then EEP is equal to E. So you know what to do over here. Now for the use of, the reason why we have come up to this point is that now we have the EEP, which is the modulus for the elastic plastic conditions, which is similar to a tangent modulus. This is the tangent modulus which is used in the element formulation rather than the E, which is generally used as a material definition for a linear case. And this provides the tangent stiffness matrix. So we can say that finally, it's very important here, the KT that you look for, which is the tangent stiffness, can be given as, if you remember from the definition, the material definition B transpose, which consists of the derivatives of the shape functions, times the E, which was the material definition, and the B again times dV, because this is a volume integral. Then in that case, this E can be replaced by this elastic plastic modulus instead of simply the linear one. So once you have changed this or made this substitution into the tangent stiffness of your problem, then you can use this relation for finding out your incremental stiffness or incremental tangent stiffness under a certain deformation which is applied, or even a change in deformation which is applied, and the change of force, or in this case I can write as dr because I've been using yield function as f. Then I can use the dr as a change in load, and because of this you have an update in your tangent stiffness, which is now related to your elastic plastic material over here, making it a non-linear problem, which includes both a strain hardening and flow hardening behavior over here. So work hardening and strain hardening is included, as well as your flow rule is also taken care of in these cases. So this is the definition of how it is involved in the nonlinear finite element problem.